først introdusere Alexander Biebricher fra NAROM og hans foredrag.
Ja, takk for det. Ja, takk skal dere ha. Først og fremst så vil jeg takke for at jeg fikk anledningen til å komme hit. Og jeg skal ta den der biten opp på norsk før jeg switcher til engelsk. Jeg jobber på Andøya. Andøya Space Center 1000 kilometer nord herifra. På en Space Center, rakettoppskytningssted, men også mye mer som skjer der. Både bakkeoppbasert instrumentering som radarer og lasere og sånne ting, som undersøker atmosfæren da. Jeg jobber ved det nasjonale senteret for romrelatert opplæring, som en slags utdanningsbit av det hele, og vi prøver å formidle da til både studenter, også litt yngre studenter, og enda litt yngre studenter, altså elever, og også da lærerne litt grann om dette her med verdensrommet. Så takk for at jeg fikk komme. Takk til Nordic Zero, som et prosjekt som vi har sammen med den europeiske romfartsorganisasjonen ESA, som har sponset det foredraget, som gjorde det mulig at jeg kunne komme. But now I think I've said too many official things. I will switch into English because I know that not everybody here in this room understands Norwegian well enough to follow everything I'm going to say. Is it okay for those of you from Norway that I speak English the rest of the time? I would suppose that it's science. The language of science is after all, English. And the title of this is called Mathematics and Human Imagination. And for those of you who expect me to become very technical about maths now, well, I won't, because it says in the subtitle, A Tale About Knowledge. So I'm going to actually be a storyteller now. I'm not going to try to impress you with my mathematical knowledge. I'm going to try to give you, that's quite a lofty goal, but we'll see whether I manage to do that. I'll try to give you the talk that I should have had when I was a physics student. It's about the big picture. A lot of what's going to come towards the end, I think you probably know about, but I will put it into what is hopefully a new perspective to you. So let's just start right now. And we say, as a lot of people do, that human imagination is boundless. And the physics students, of course, say, well, go ahead and imagine gravity then, right? There's several ways of imagining gravity, gravitation. And one of them involves this, for example. You just have some sort of cloth that is bent downwards, and then you have, for example, planets orbiting around the sun there. And as they start colliding, those planets, which the real planets thankfully don't do, you'll see at one point that they all start also rotating in the same direction. So why? I mean, that would be a way to imagine gravity. It's some sort of cloth that is bent, you know, the fabric of space-time, as they say on TV. By the way, we can start bets whether Lawrence Krauss tomorrow will use the expression fabric of space-time. But it's some sort of cloth being bent. What they never say on TV is that that is actually wrong, of course. And it's very simply wrong because it's a two-dimensional thing that's bent into a third dimension, while Einstein's space-time has four dimensions. So there's a little bit of information that the folks on TV leave out, right? Or this.
Gravitons are the as-yet undiscovered force carriers for gravity. Because of the great success of the Standard Model in describing the other three forces which exchange bosons, it is assumed that gravity has a gauge boson as well. Its properties have been extrapolated. It is a massless, stable, spin equals 2 particle that travels at the speed of light. Gravitons may not be constrained to the dimensions of space and time that we experience.
I love that little video clip. It's a fantastic accumulation of incredibly weird words. But there's one sentence in there where it says, gravitons may not be constrained to the four dimensions of space and time that we know of. If you listen to Brian Cox on TV, he doesn't say that, right? He just talks about, well, you know, the force carriers for the electromagnetic force, well, it's a photon, and there's this particle for the strong nuclear force, for the weak nuclear, blah, blah, blah. There must be a graviton. But here's the thing. I mean, you study physics, you study maths, you're into the whole thing, and to you, after a while, these expressions, these formulations become normal, right? And with good reason, too, because we get stuff like this that we can see in this case, the southern sky. This is so-called Einstein Cross, which is, well, what is this? It's actually a galaxy here in the center, which bends light out of line from a source behind the galaxy. And depending on the mass distribution of the little fuzzy galaxy here, you either get a whole ring or bananas, or in this case, the little 4 points of the Einstein Cross. If you leave this room here, if you leave Realfagsdagene here at NTNU, and you talk to so-called normal people, how do you explain that, right? It's real. I mean, it's very real. We can see that. How do you explain it? Well, maybe you try this. Oh, see, I have kids, right? They stand in puddles, and if the puddle's clear enough, which it never is, but let's assume it is, you know, they have parts of their legs looking like they are bent forward, right? And you know that too. If you stand somewhere in the water, the lowest part of your legs and your feet, they look like they're kind of bent forward. But that's decidedly not what it is, right? What it is this. You have the fabric of space-time with the source behind the universe here and the galaxy here in the front. And the light is kind of bent into the curvature or follows the curvature of space-time. But again, as soon as you use that picture, you're actually slightly lying, right? Here's the cloth again. And if you look at that, and if I look at 80 people coming from all over the country to come here, I'm actually quite glad that there are so many of you who choose to study science in some form, physics, maths, or whatever it is, because here is a quote that I'll just try to, on the go, to translate. This is Norway's Prime Minister, Erna Solberg, coming to Andøya in 2014 to the opening of what is called Spaceship Aurora, a spaceship simulator we have there, behind the mountain somewhere. And she says, it's magnificent and beautiful here between the heavens, or the skies, the ocean, and the mountains on Andøya. What you work with here at Andøya Space Center is at least as magnificent as that, but to me a little bit, well, not mysterious, but mystical, right? And that is rocket science. Think about that for a second, right? The Prime Minister, now don't tell her that I have put that slide up there. Through many corners, she actually pays my salary, so. But you have a Norwegian Prime Minister in 2014 saying that science is mystical to her. And my point is not that I want to say bad things about Erna. What I want to say is it really something that we should be surprised about? Because on TV, we talk about gravitons, we talk about cloths being bent out of shape, call it the fabric of space-time, and nobody really knows what it is, right? So let me take you around a bend in the street and show you a picture of my daughter when she was 1 year old. It's okay I show that picture. She doesn't look like that anymore, so you won't recognize her. But is anybody here who can tell me what she's just done? There's a table there, right? It's empty now, right? I can tell you there was she pushed something off the floor. There was a Lego giraffe that was sitting here, and she just snipped it over the edge of the table. What I don't show you in that picture is Daddy sitting here to the left on this floor, being totally prepared to just put it up again for her to push it down again, right? Now here's the thing. She's obviously experimenting, right? But does she know what gravitation is? That's a weird question, isn't it? Of course she doesn't. But do you know what gravitation is? Is there anybody who dare say yes after all I've just said? Okay, me, I say yes. So here's the thing. I have a little laser pointer here. I'll get close enough. I want to throw it at the clock here. Would you trust me to at least get close to it? I won't say I hit it because I'm not that good a thrower, but who would say, right? I mean, I would get close to it. Now here's the thing, and now the physics students come in. If you really think about what controls the flight of this object towards the clock, how can I get near that clock if I don't know on some level what gravitation is? It's gravity, unless I don't throw it so fast that air resistance comes into play, is what controls the flight of that object and its rotation and everything. But still, you get the point, right? On some level, you kind of have to know what gravitation is. Yeah? How can you know it? Well, maybe it's because gravitation is part of the nature around us, and this is just, me speculating here, but maybe it's because nature includes gravity. We're used to it. Without it, we just aren't here, right? So we have to have some knowledge of what it is. And in fact, one of the first things the kids, when they grow up, what they try to find out about is gravity, just like my daughter. And I think everybody comes out, starts living, and is actually a kind of researcher, curious, wants to know things. Thankfully, a lot of people keep their curiosity, maybe even like you guys. Again, I like the fact that there's so many of you here now. We keep our curiosity. You kind of have to want to know how nature works, or you have to know how, you want to know how things work so you can build something out of it. There's a certain element of curiosity there. And I think we can explore that a bit more, because what I'm going to do now is I'm going to look at that telescope, and I'm going to choose astronomy as my case to show you what I think maths is. Now, I will be very clear about something here. I will sound as if I know what I'm talking about. Totally, right? I mean, I'm a doctorate in physics. I have to know what I'm talking about. But the actual point of it is to get your thoughts going, right? So it's not about me telling you it's like this. It's about me saying to you, is that guy there in the front right or isn't he? So we're going to use astronomy as an example. And astronomy, somebody calls the oldest of all sciences because it goes back, I don't know, we can trace it back to 6,000 years before Christ or something like that. The Babylonians, measured or tried at least to keep track of the stars' movements, what the Greeks would call the wandering stars later, the planets, the sun, of course. All of that was written down. The Chinese were meticulous for over a millennium to just write down what they saw, but they didn't write down very much what they thought of it. So we don't know. And then there's my favorite story about Ra, the god of the sun in Egypt. I don't know whether you know that story. Ra had to go down to the underworld every single day, and fight a basilisk there, so that the sun could come up the next day again. Now, the problem with Ra, the mighty sun god, was that he wasn't quite strong enough to beat that basilisk on his own. So the pharaoh had to go down and help him, right? I mean, if I'm the ruler of a country, what a thing to take credit for. Hey, the sun goes up again or comes up again the next day, right? So it's a bit mystical. It's about gods. It's about stuff like, I don't know, when this particular star comes up, over the horizon in this particular angle, then it's the right time to sow your seeds in the acre or something like that. So these two elements to astronomy there. It's not really a science yet. But at one point, we could start measuring things. And we go to the Hellenistic culture now, to the Greeks. And what they did basically was to say, I have a piece of length. And from me to you, there is a distance of a certain amount of these pieces of length. They started measuring things. And as soon as you start measuring things, you have the common ground to actually talk about something. There's no high priest telling you what is true. You can discuss ideas. You can discuss measurements. And that is what came in there and what is new. And I want to pause here and just point out one particular very interesting person, and that is Ptolemy of Alexandria. Now, all of you, I hope, will become scientists. And just think of this. The guy worked for his life, did science, right? Or something approaching science in some ways. I don't really know actually whether I should call him a scientist, but what he came, like let's say parts of his results, part of what he studied, part of what he found became dogma for 1400 years in some parts of the world. That's about the ultimate success for a scientist, right? You find gravitational waves, and there's nobody who says that what you've done is wrong for over a millennium. Right? So let's look at the guy and let's look at how he thought, because this is 100 after, or 100 AC after Christ, we're talking about here. And that is a time when we did not have the concept of forces. The most elementary thing in some ways that those of you who study physics actually are perusing at the moment. How do you explain the world? On what base do you explain the world if you don't have a concept of forces? How do you explain what stars do and the planets do? You talk beauty. Actually, you talk beauty. What is beautiful has to be true. And what is the most beautiful geometrical construction there is? Well, a sphere or its two-dimensional counterpart, the circle. And it is to the credit of Ptolemy that he could explain everything he saw. I'm sorry about the microphone that I just touched. Everything that he saw, he could explain with the help of circles and spheres. So let's just start. The first thing was that the Earth is a sphere. Right? And he found that, for several reasons. I mean, first you have the movement of the stars, of course. There is a center point to that movement that is not at the same height over the horizon if you move from north to south. So let's say you go along the Nile Delta, that point moves a little. And then there's this picture, of course, the actual existence of the horizon. And I have this picture, I mean, this is too obvious to actually talk about, but I have this picture in the presentation because I stole it from a website called flatearthsociety.org. Those of you who follow the internets and Neil deGrasse Tyson and some rappers in America know that I don't have to talk too much more about flat earthers, but I thought that's too beautiful, right, to not include, right? This is a picture from the Flat Earth Society. But so he found the Earth had to be a sphere. But that raises a question. If the Earth is a sphere, how is it fixed in space? It just hangs there. And then something very ingenious happens. The guy has an assistant somewhere south in the Nile, along the Nile, and he's himself in Alexandria, takes up a piece, or just a little bit, a piece of Earth, basically, lets it fall, falls downwards. Now, he knows we're talking a sphere here. His assistant does the same thing several thousand kilometers away to the south. The piece of Earth falls down again. Well, if everything falls down towards the center of the Earth, we don't have that question at all. The Earth doesn't need to be fixed to anything if everything falls down and is attracted to the center of the Earth. So that's fine in some ways, but you still have one problem, and that problem is, how do you explain the star trails, right? The movements of the stars. Something had to rotate, and there were actually just two choices. One of them was the Earth rotates, the other one was the stellar, what is it called? The stellar sphere, the heavenly sphere, I don't know, something like that. Some sort of sphere with the stars on it actually would rotate. Now, I'm not sure here, because I don't know how Ptolemy thought about this, but he concluded that the sphere rotated, which is very interesting because we know that Ptolemy knew that the heavenly sphere was far away, very far away. And how do we know that? Because, well, first of all, we do know quite a lot about him, but he had made some experiments on the intensity of the stars, both in Alexandria and south along the Nile River. And if those stars were close to the Earth's surface, their intensity, the intensity of the same star should vary from Alexandria to the south of the Nile River. Do you understand why? It's like if you think about the geometry, right? You'd be on one of these places, you'd be much closer to the star than at the other, so the intensity of the light should vary, but it didn't. And the only way you can explain that is by saying the star sphere or the heavenly sphere is very far away. rotates, even though it is far away, and it is big, which is the consequence of thinking that. It's big, it rotates very fast because we know it rotates around itself once per 24 hours, right? And this is just trivial physics, actually. If you think about the equations here, and if you think about if something rotates as fast as that, or if something rotates once around itself in 24 hours, it's humongously far away. It has to be really fast. And there, the whole thing stopped for Ptolemy. I don't know really what he thought, but I have one more thing about him, and that is also something quite ingenious. I hope the animation will start working. No, it doesn't, so we go back, try it again. No. Doesn't. Well, what I was supposed to show you here was parts of the orbit of Mars. I'll try once more. Just one more time. Let's go back. No, it doesn't want to come. And what it's supposed to do is to make some sort of loop here on the sky. It's called retrograde motion. And the planets do that, or some of them do. And to explain that is difficult. If you think there's a heavenly sphere with everything on it, and everything is supposed to be explained in circles and in spheres, because that, again, I'll trace it with the laser pointer, that loop is decidedly non-spherical. But Ptolemy's idea was that, well, here we have the planets going around the Earth on a circular orbit, and then there's a little circular orbit or a little circular motion on top of that. It's called epicycles, and that's ingenious, really. You have no concept of forces, and you say, this is what I think the world looks like. And why? Right? What is beautiful had to be true, and Ptolemy could, make no mistake, he could explain every single measurement, every single observation that was made at his time, given the accuracies at which these observations were performed. What is beautiful had to be true. So now I'm going to do something that's a bit facetious in some ways and not quite right. I'm going to just jump over what the Arabic world did in terms of astronomy and just hop a century or a millennium. It's not right. They gave us a lot, basically, everything from the numbers, the way we write them today, a lot of mathematics, a lot of new ways of measuring the positions. But at the end of it, you'll understand why I hop directly, I hope you'll understand, to Nicolaus Copernicus, who was not the first man, to think that the Earth could not be the center of it all. I'll give you another example from the Greeks. Good old Pythagoras had a fantastic way of looking at the world. He thought that there was the Earth. The sun went in orbit around some common center, right, which was a fire that was conveniently invisible, right? But there needed to be an anti-Earth. So that was his idea, right? It's fine. Copernicus had a different idea, and Copernicus's problem with Ptolemy's ideas was very simple. I actually told you already. If the heavenly sphere is as big as it's supposed to be, what is it made of if it rotates that fast, right? So he said, no, I think the Earth itself rotates. And he started looking at old measurements. He made some measurements himself, put everything together. He's also one of those guys who looked at what's called relativity, which is to say, just the idea of, you know that, right? The train and the platform and the observers in the train and on the platform when you just look at how they see each other. Copernicus looked at similar examples as well, and then he put together his own view of the world with the sun in the middle and the heavenly sphere around it. It's very often forgotten that he still had a heavenly sphere included in his model. But most of all, there was still, everything done in circles and spheres. Only that the heavenly, and Copernicus was a pious man, the heavenly object in the middle now was the sun that gave us warmth and life. And then, of course, we had the 17-year-old from Denmark called Tycho Ibrahim, who in later years would assemble what is probably the greatest assembly of astronomical instruments that was ever put into one place in Uranienborg his own castle that he got for his observations. He had everything apart from a telescope, and he measured. And there's data from over 20 years of observation. But Tycho himself found something's wrong about it. Something is wrong. He couldn't quite put his finger on it. He tried to have his own view of the world and his own system of the world, but he couldn't quite pinpoint what it was. So on his deathbed, he gave all those 20 years of data to a young German scientist called Johannes Kepler, and these figures you have seen before. Kepler studied, in particular, one planet, Mars, who has a slightly more elongated orbit around the sun than the other planets do, and found out that the planets orbit around the sun with the sun in an elliptic shape with the sun in one of the the focal points. And that's different, right? And it's not as easily, it's no longer like beautiful, quote unquote. The perfect circles were stretched a little bit. And you know Kepler's laws quite probably. So there is also a little bit of maths coming in when we compare the orbits of two different planets. And this is, by some definition, where physics starts in the sense of describing nature with the help of maths. And the next one in our series of people that we talk about is Isaac Newton, of course. And Isaac Newton, who, let me say it directly, did not invent calculus. Neither did Leibniz in Germany at the same time invent calculus, as if the rules of calculus hadn't been there before they were actually starting to work with it. Right? Boom, there they are. No. It's not what happened. They discovered, I would rather say. But we're going to focus on Newton because he did much more with these rules of calculus at the time. And he looked at that apple, or whatever it was that he let fall, and to him something curious occurred, and he just saw this also, and that is, if you let something fall from a higher plane to the ground, it hits the ground faster, obvious. But no matter how high you went, it always fell down. So whatever it was that attracted the object downwards, well, it could essentially go weaker if you go higher up. Okay, fine. But it would never stop having an effect. And that meant it should also work and have an effect on the moon. The moon had to feel gravitation, as we now know it's called. And he started making calculations about it and found out, of course, and you know that the moon actually tries to fall down to Earth but never hits the Earth, right? That's what it is, because it has enough horizontal velocity to go in orbit. But that's the whole point here. He sat down, he worked it all out, discovered new mathematics, right? And found the rules of the universe, nothing less than that, as it was known then. And for those of you who are mathematically inclined, I know that equation is not completely complete the way it stays there, but that's not the point, right? But the point is, the guy sat down, he started calculating, and at the end, something as short as this came out to explain the universe, huh? How great is that? I was a theoretical physicist before I became a science communicator, and I always dreamed of that. That's like sitting there in your office, right? The whole lone genius thing, right? You sit in your office for a couple of years, and then you come to the world with your couple of letters. This is how it works. Mathematical catharsis. It's like building your own house, right? Everything. You build everything, and then the first sip of coffee on your new sofa in your new house. That's how this feels, I would imagine. I've never got there. And I think, and I doubt highly that Newton felt like that too. The guy became an alchemist at age 26 after he came to that point. And most of all, he lived in the 1600s, 1700s, and at that time, maybe the idea of this being such an idealistic pursuit was sometimes a bit dangerous. I have a very small picture of Galileo here, who had to defend himself rather directly for what he found. I mean, he had a telescope, and what he found was that the heavenly sun had spots on it. That perfect sphere with spots on it. The moon had craters, right? Saturn had rings and Jupiter moons. Nothing was beautiful in the old sense anymore, especially the sun, right? But then look at this. So Stephanie, just in case you wondered why I asked where you came from, the guys who make these kind of videos, they sit at NASA Goddard, where she comes from. So if you know them, or if you happen to know anybody who knows them, please give them my regards. They are a wonderful tool for people like me, right? Because there it is. You cannot look at this, I would assume at least, and say that the sun isn't beautiful, right? And maybe what's beautiful is not what's true, but what is true is beautiful in some sense. And I can go back to Newton here, who as a 17-year-old, before he even started thinking about the universe, looked at rainbows and said, that's odd. Where should these colors come from? Right? And he set up an experiment with a dark room with a little hole in a door, a prism, and you would see the colors of the white light. And here especially, I want you to stop and think for a second, right? For you probably, if you've taken physics at school, you started studying physics, that's about the most normal thing there is. But go back to the 1600s now, and as Neil deGrasse Tyson put it, it freaked out the artist of the day, right? You take all the colors on the palette that you try to paint with, you put them together and it becomes white. That's odd, that's really odd. But it is also the basic for most of what we know about the universe, because it is the basis for a way to explore the universe, right? And I don't have to talk to you too much about what colors actually are. They're just wavelengths. They are measures for how much energy sits in a particular electromagnetic wave. And we can use that because we could put up so-called specters, or spectra, I should say. Like here, for example, the spectrum of the sun, which has some places in it, some wavelengths where the Earth's atmosphere absorbs a lot. So if we want to know how the atmosphere, what kind of elements are in the atmosphere, we can actually look at what kind of wavelengths are taken out. And before we move on, I just want to point out that may be interesting to you. This is the so-called black body spectrum, of course, and it has its maximum smack in the middle of what is the visible range for human beings. Just a slight question to the side. Do you think that is quite, what's the word, coincidental? Is that a coincidence? Yeah? No?
Our eyes obviously evolved to see the...
Exactly. Yeah, exactly. Our eyes have evolved to that. It's also one of those things that you have to make yourself conscious of, even though it's a rather simple fact in many ways. But yeah, the elements and molecules in the atmosphere and in the universe, of course, they have quantum mechanical energy states connected to them, which means you have a sort of barcode that you can use to see what's there. And it's in this way that we know that most of the visible matter in the universe is hydrogen. And of course, I wanted to show you a picture that had a lot of red in it. I don't see it from here. Maybe from the different angle. You see a reddish color here in the Horsehead Nebula. It's hydrogen, right? So we know that from these kind of examinations. We also know with the help, and I forgot to say that, but it's spectroscopy I'm talking about. With the help of spectroscopy, stuff like that we are part of a galaxy with 400 billion stars, I think is one of the estimates. That's 100 to 120 light years across, which we know while being in the middle of it. Just think about that for a second as well, right? We're in the middle of that heap of stars, and we know all these things. We also know that most of what's around us moves away from us because the barcodes of the elements don't exactly align. What we actually, this is probably, we should see lines like this. We don't see them. They're slightly moved towards the red colors or the less, or the lower energies, so-called redshift. So we know everything apart from the Andromeda galaxy, which will collide with us in a couple of billion years. So don't sell your house or just yet. But everything else is moving away from us. And that means And this is also something you're going to hear on TV. And that means that at one point everything was together in one place and time. That's a rather big conclusion. Why didn't the universe have some sort of extension in all directions to begin with? And then it started moving all apart. Why do we know that? Well, we do know that because of these. These are Einstein's field equations. Just going to read up that sentence below, especially for the math nerds amongst you. The Einstein field equations are the 16 coupled hyperbolic elliptical nonlinear partial differential equations that describe the gravitational effects produced by a given mass in general relativity. When I was a student, and I heard for the first time 16 coupled hyperbolic elliptical nonlinear partial differential equations, I swallowed, I hid in the closet for a couple of weeks, and I didn't want to come out. This is difficult to solve. And the fact is, and I hope you know that too, there are no solutions to this that are valid for all the different parameters. The parameters here are time, the space dimensions, velocities, mass of an object in that field, in that gravitational field, stuff like that. There is no solution that covers the whole range. But how do we know then that there was a Big Bang? Of course, that's what I was talking about with the point in time where the universe was centered around one point. Turns out we have a solution when we assume the time parameter in these equations to go towards 0. And it turns out that, and that's basically just an estimate really, but we think we have a solution for that case, but we don't have a solution at t equals 0. It's what is called, it's a mathematical singularity, as it's called, and it's the solution who has that singularity, not necessarily these equations. Our approximative solution has a singularity at t equals 0, and that's why we think, well, something has happened there. But we don't really know, really. But if you follow that particular solution or approximative solution to the equations, you actually get the whole inflation thing. There are more solutions to or approximative solutions which are valid under different circumstances, like, for example, the whole black hole thing. We have a solution for the case when the mass of an object in space-time becomes very big. We don't have a solution for the center of a black hole, where they say on TV the mass is infinitely big, time stops, space makes no sense, right? That's Michio Kaku here, by the way. But we do have an approximative solution that goes where the masses become very big, and of course those are black holes, right? And here it's worth making a point, and that is the guys on TV, they actually know what they're talking about. They meet people who tell them, journalists for example, who tell them, can you explain a black hole to me in 5 seconds? No, I can't. I need 16 hyperbolic, elliptical, partial, non-differential equations, whatever. I can't do that, but they try, right? And that's where the cloth comes in, right? That's why they use things like the cloth, the two-dimensional thing, the fabric of space-time, because you can represent it by a cloth. But once the camera stops rolling, they actually know what they're talking about. They stop talking about black holes in them. They stop talking about black holes. It's all about stuff like perturbation theory, about boundary layer theory, and other mathematical approximative theories. It's about the math all of a sudden, because how else do you want to approach that, right? Here's a part of Einstein's equations written out. That looks wonderfully absurd. But if you really think about what I've been telling you, we started with the whole mystical idea, gods, practical stuff, sowing seeds on an acre and stuff like that. Then we started measuring things. We looked at the beauty of the whole thing. Then maths came in, right? And at the end of it, spectroscopy. We went from something that was very, and I mean literally very down to earth, when do I sow my seeds in the acre, to something that you can't really imagine now, right? Quantum mechanical energy levels of atoms. How do you want to imagine that, right? So what I'm proclaiming is, and I'm I'm just claiming that, I should rather say, is that human imagination is not boundless. Here's the title page again, and I hope you've realized that I've put some geometrical forms there. Because if anybody ever says to you, that's not true, here's the example to give them. What is a square? It is a geometrical figure where all the sides have the same length, right? Its three-dimensional equivalent is the cube. Anybody know how the fourth-dimensional equivalent of that looks like? Oh, I can show you the projection of it into 3 dimensions, projected into 2 dimensions on that canvas up there. It's called a tesseract. Ask people to imagine a tesseract. Yeah? And if you haven't read it, just on a side note, read Flatland by Edward Abbott, because there is a discussion of why we cannot imagine that, no matter how much we try. However, we are not helpless, right? We still have those hyperbolic, parallel, whatever, 16 equations, right? And we use them. So I want you to start thinking about what will be my point in about 5 minutes, because before I get to that last slide, I just wanted to show you that human imagination may have bounds, but it tries to catch up to the maths. Because I'm going to show you a video of a man who suffered from insomnia, a musician, who thought he'd make music about a mathematical singularity. If you don't know about them yet, they're called Symphony of Science. There's masses of videos like that on YouTube. And the guy is called Boswell, I think, lives in Washington State in the US. This was about a mathematical singularity. And what's on the screen right now is a sentence in the region that reads, maths is nothing less than the most powerful tool we have in our toolbox when human imagination is at its end. And if you are like me, as a student, I can almost promise you that you will run up against the wall when it comes to mathematics at one point in your studies. Don't worry, fight on, because boy, is it worth it, right? It's our way to describe nature, right? Thank you very much.
Many editions, and I'm happy to say that we're actually so delighted that it's used here at Trondheim that the latest edition has Norwegian content right on the cover. You actually see the Leonardo Bridge right here is actually prominently displayed, so everyone will know in the world that physics and Norway go together perfectly.
So one of the biggest questions that we are striving to answer, especially at NASA, is where did we come from? Are we the only ones there? In the universe? Is there any other life out there? If so, what does that look like? What kind is it?